Now, let me start by doing some problems related to linear and quadratic approximations of functions. And this naturally leads to higher order approximations, which finally leads to the Taylor series. So Taylor series is a general formula which give you any order of approximation, and you can truncate it to any given order which you like, and that would be the order of your approximation. So for you, this is just a reminder that the Taylor series of any function is given by Taylor series of f of x. People call it at or around a point, but sometimes people also call it near a point. X is equal to a. And all you need to remember is this formula, that you evaluate the function at this given point. That's the lowest order, that the function is just this value, a constant value, but functions are not constant. So then you have the next order, which is the function represented by a line. And this is the slope of the line, the derivative of the function at this given point. And then you include higher orders, which involve second derivative, third derivative, and so on. The nth order term is just this, which has the nth derivative evaluated at a and keeps going. So let me write here where f of n, a, is the nth derivative of f evaluated at this point a, where you are doing this Taylor series. So we had done many examples of it. Let me do another example. Let's take it as a problem. Find the Taylor series. We hadn't done it in class. We had done it for the sine of cosine of x at x is equal to 0. So all you need is, so this is the solution. Cosine at 0 is 1. So that's this thing which you needed. And so this is the f of 0. Then f derivative of x is minus sine x. And when I evaluate it at 0, I get a 0. F double derivative of x is minus cosine x, because I'm taking a derivative here. And when I evaluate it at 0, I get a minus 1. Then the third derivative gives me a plus sine x, and that evaluated at 0 is again 0. So there's a pattern. Cosines turn into sine, sines turn into cosine, and every time I evaluate sine at 0, I get a 0. But when I evaluate cosine, I get a 1 or minus 1 because the signs also alternate. So this is the fourth derivative. Gives me a cosine. Zero is again 1. So I have alternate pattern. And then I find that cosine of x is Taylor series is 1 minus x squared. This minus came from here. The linear term, let me write it term by term. The second term is 0 times x minus 0 plus minus 1 times x minus 0 square over 2 factorial plus 1 x minus 0 4 factorial and so on. So where this is f of 0, f derivative of 0, and this is your point A around which you are expanding. Similarly, this is f double derivative of 0, and this is still your point A. So this gives me 1 minus x squared over 2 plus x4 over 4 factorial minus x6 over 6 factorial and so on. So from this equation, you can say that the linear approximation of cosine of x near x is equal to 0 is that you only have to consider powers up to 1, up to first power. Take only powers up to 1 of x. So that means cosine x is just 1 near x is equal to 0 in linear approximation. And if I
repeat this part,
yeah, because yeah, so
powers up to 1 of x. What does that mean?
well, if you look at the Taylor series, you always have different powers of x in it, increasing powers of x. If you include less and less powers, you start from the first power. If you only take up to power 1 of x, then that's the linear approximation. If you include up to power 2, that's the quadratic, and so on. If you include up to power 3, that's cubic. It just so happens that up to power 1, if I include up to power 1 of x, there's no term here with power x to the 1. So the only thing I have to include is 1. And this is very intuitive because remember, in linear approximation, you are approximating the function with a line. And near x is equal to 0, if I look at the graph of the cosine, it's like this. So over here, the line which is tangent to it, which I am approximating around here, the cosine looks like a straight line, which is a horizontal line, whose equation is just this. So therefore, cosine x, it just becomes, so not x is equal to 1, y is equal to 1. So that's the equation And that's what you found using these formulas. If I write the quadratic approximation, of cosine near x is equal to 0, so then I have to include up to second power of x. So that means that cosine of x is 1 minus x squared over 2. That's the quadratic approximation. But this is only near x is equal to 0. If you want to find an approximation near some other point, then you will have to expand it around that point. So let's do it around let's do it around pi by 4. So let's say problem. What is the quadratic approximation of cosine x around what is, let's say, quadratic and linear? Let's find both. Of cosine x around x is equal to pi by 4 at 45 degree. So at 45 degree, it's not going to be 1. It's going to be, the linear approximation is going to be some line like that here. And the quadratic approximation is going to capture this part of a parabola, some parabola. So again, if I find the Taylor series, the complete Taylor series, around x is equal to pi by 4, the derivatives are same. They go like this, but now I'm going to evaluate them at pi by 4. So I have f of pi by 4 is 1 over under root 2. Is that true? What's the cosine of pi by 4? Hmm. 1 over under root 2, yeah. So this is 1 over under root 2. And then I find f derivative. That's, so f of x is cosine x is minus sine of x, and at pi by 4 is minus 1 over under root 2. And f double derivative is minus cosine of x, and when I evaluate it at pi by 4, I get minus 1 over under root 2, and so on. So I can write the whole series, but I don't need it. Let me write it up to second power. So cosine x starts with this guy. 1 over under root 2 plus the derivative evaluated at this point, which is minus 1 over under root 2 x minus this point pi by 4 plus the derivative, which is still minus 1 over under root 2 and x minus pi by 4 square, and you have a 2 factorial from the formula. So the linear approximation, you will retain these two terms. And it's representing a line, this line which I drew, this line, and it has a slope minus 1 over under root 2, which makes sense because it's a negative slope, as I was expecting. And if you include all of these, this is quadratic approximation. You do not miss this piece. When you are writing the quadratic, you include the next term, the square term, but you do not leave the previous terms which you already had over there. Now let's do some applications of these things from, let's say, from the book. Or let me say, let's compute. Let me see if what I have given in the homework. Okay. So suppose I want to find quadratic. Let's say first, let me just find linear approximation of x squared. So all I need is the first derivative. One plus x squared, then by chain rule, x squared, then 2 times x. That's the derivative. Linear approximation near x is equal to 0. So now I evaluate it at 0. I get a 1 from here, a half, a 1, and then, but this guy kills it completely. So linear approximation is not very interesting. Linear approximation is log evaluated at 1, at 0. So log of 1 is just 0. So that's the linear approximation. Y is about 0. To get anything changing, to capture anything changing, I have to go to the second derivative. So f derivative of x is from here, 1 plus x squared. So double derivative x squared minus x 2x. Now when I evaluate it at 0, this term goes to 0 and this term gives me a 1. So that means that log of will be 0. That's coming from here. Plus 0 plus this derivative 1 x minus 0 whole square over 2 factorial. So it's simply x squared over 2. So logarithm of 1 plus x squared goes like as if it's a x squared over 2. Let's look at these problems. So it asks you to evaluate this is problem 23 from exercise set 3.10. So evaluate 1.999 to the 4 by using linear approximation. So I should choose some point where I can compute this fourth power easily and which is close enough to this actual value so that I hope that my answers will not be very different from the two answer. So if I consider what I'm doing, I want to find the fourth power. So consider this function x to the 4. Then I need to evaluate it at x is equal to 1.999. This is my exact task. But I don't want to take fourth power. Suppose I don't have a calculator at my hand. So to do this, I will have to take this number, multiply with this, get an answer, then again multiply with this. Will be a very long multiplication. So I just need an approximate answer. So find a linear approximation of x to the 4 near
Another question.
x is equal to 2. So I chose x is equal to 2 because I know what is 2 to the power 4. That would be very easy to evaluate. On the other hand, 2 is also very close to 1.999. So I am hoping that the errors will not be large. So linear approximation, for that I need f derivative, which is f of x cubed. And as per my formula, since I'm doing it near 2, so I have to evaluate this derivative at 2. 2 to the 3, which is 8. 32. So that means the linear approximation of x to the 4 is x evaluated at 2 plus f derivative of x, f derivative evaluated at 2 x minus 2. That's the formula. So I just put in numbers. Sorry, this x4 evaluated at 2, the function evaluated at 2. which is x4. So 2 to the 4 plus this derivative, which I have already found, 32 times x minus 2. So I get 2 to the 4, which is 16, plus 32, 2 minus, and x minus 2. That's the linear approximation. So I needed this value, which I can find by a simple calculation. So this is minus 0.001. So very easy to do. 16 minus 0.032. And you can just do it. Gives you a very good idea. Whatever you get. 15.96, whatever, you can do it.
Then should the linear and quadratic approximation give the same result?
No, they won't give the same result. Quadratic and linear will give you different result. Quadratic will be closer to your true answer. The more powers you include, the better is the approximation.
Also, sir, why did we use 2 over here if we would have used any number greater than 1.99? ज़्यादा बड़ा number ले लेते अगर 4 या 5 तो approximation गलत हो जाती है.
दोबारा ऊंची बोलें, आवाज आपकी बहुत कम आ रही है.
अगर 2 के बजाय हम लोग ज़्यादा बड़ा नंबर लेते 4 या 5 तो approximation सही नहीं आता.
हाँ, approximation सही नहीं आती क्योंकि हमारा आंसर जो था, हमने वैल्यूएट इसको करना था अराउंड 1.999. तो 5 से अगर मैं 5 के अराउंड अगर मैं इसको एक्सपेंड करता, तो ये जो डिफरेंस है, जितना आप दूर जाएंगे अपने पॉइंट से जिसके ऊपर आप अप्रोक्सीमेशन ले रहे हैं, जितना दूर वैल्यूएट करेंगे उतने ज्यादा एरर्स आएंगे. तो इसी तरह जैसे इसमें ये हुआ है, लेट मी सी. Square root of 99.8. Evaluate by using, this is a problem, linear approximation. Now again, I know that I can very easily compute the square root of 100. This is 10. This will be hard if I want the exact answer, a very complicated procedure to find it. So instead, I consider this function. I'm evaluating this function and need this value. .8. But my strategy would be to expand it, linear approximation, near x is equal to 100, because at 100 I can find the linear approximation with good, with easy evaluations and good numbers, and it's close enough to 99.8. Since it is easy to find, easy to evaluate different terms in the approximation at x is equal to 100. Also, and this is crucial. This point is near 99.8, where we need to evaluate the function. So let's just do it. F of x, first you have to evaluate this at 100, and then you have to compute the derivative evaluated at 100, and just multiply with x minus 10. Not 100, at 10. Well, 100, sorry. 100 and 100 here. X minus 100, the point where you want the linearization. So this gives me under root of 100 plus the derivative of the square root function, which is this 100 x minus 100. So this gives you 10 plus 1 over 20 x minus 100. So now I can evaluate 99.8. It's going to be about 100. So 10 minus 0.0 2 over 20. So 10 minus 0.001. So you get 9.999. Let's look at some more related problem, which actually I was trying to do in the class.
Sir, can you also do some trigonometric examples like 1046?
1046. Well, I just did a cosine example, so tan one you can do yourself. I just did this cosine at x is equal to 45. Remember, when you are doing this, because the derivative of cosine is sine and derivative of sine is minus sine and derivative of sine is cosine only if you use the radians. Because the limits we had computed when we were computing these derivatives, we had assumed that we are doing our calculation. Those limits only came out under the assumption that you are measuring the angles in radians. So remember, if you're trying to find it at 45 degrees, here at x, you won't be putting 45. You will be putting in a radian angle. So for 45, you will be using pi by 6. Similarly, if you want 46, you have to convert that into radians. So that's the only tricky part. Otherwise, you're just using this formula. And I did it for cosine. You can do it for tangent too.
Okay, sir.
Now, for example, let's do this. This is yeah, I had written it from, let's see, did I write it from the book or did I write it myself? Yeah, it was from the book. Let's see. Yeah. Okay, so someone asked a question. Let me see if I. Well, I'm not going doing any homework problems over here. If you have any specific question, so someone said that show that for any m, the linear approximation for small x is 1 plus max. Let me just give you one hint. When I say for small x, what does that mean? That means x is close to what number? 0. Yeah, Mudassar had the correct answer. So that means you're expanding it near 0. You're finding the linear approximation near 0, and then you can do it yourself. So someone wants me find e to the 3 log 1.1 to the power 2 using quadratic approximation. So let me see which one they are asking me. So someone wants me to do this. E to the 3 log 1.1 to the power 2. Well, first of all, this is equal to the 6. So this is just 1.1 to the 6, isn't it? Yeah, I'll do some word problems as well. So this is just the 6th power, nothing very difficult. So you can consider this and find it near 1.
Sir, I have a question.
Yeah.
Can we consider this x plus 1 power 6 and consider it near x equals 0.1 or x equals 0? X equals 0.
X, so you take this and you consider it near 0. Well, that would be not a very good thing to do. Better thing is to do it near 1, because then
No, you do it. You write the expression as 1 plus x whole power 6 and take it near
yeah, you can do that.
x
You can
equals.
do that. You can do
So
that. That's
it's the
totally
same
fine.
thing, right?
Yeah, yeah, exactly. Yeah, you can
And we
write
take
this.
the nearest integer, right?
Yeah,
So
instead of
not
this
to,
function, you can consider this function.
and we have to take the nearest integer, right? Like no,
Yeah,
we can't take
yeah,
2.
yeah. No, well, you take nearest integer because if you, it depends on what job you are trying to accomplish. If you just say that, okay, if I take x is equal to 0 here, my linear approximation will start with 1 because I will know how to compute the 6th power of 1. Yeah, that's why you take it. Otherwise, there's no like a rule. It's just about what you are trying to accomplish.
Okay, sir.
Okay, now let me do some word problems related to these linear approximations. And as I had said, yeah. So it's the problem 36 from the book exercises, the same set, 3.10. It says, use differentials to estimate the amount of paint needed to apply a coat of paint 0.05 centimeter thick to a hemisphere dome with diameter 50 centimeter. So you have a hemisphere dome like this, and you want to apply it a coat of paint. So in a sense, when you apply the coat of paint, well, not in a sense exactly, you have 0.05 centimeter thickness of the coat of paint. It's not like infinitesimally thin, it has some thickness to it, and you want to maintain some kind of thickness, a uniform thickness onto it. So you want to find how much paint you will need. How much paint means a volume, certain volume of the paint. It's the paint is in your box. You transfer it onto the dome, but whatever paint you take out from here is just distributed uniformly onto the dome. So how can you find the volume? Essentially, what you are doing here is you are trying to find the volume of you're trying to find the volume of this thin shell. So we need the volume of the thin shell. This volume of the thin shell is actually equal to volume of a slightly bigger hemisphere minus volume of the original hemisphere. So you can exactly find it by doing this. The radius of this hemisphere is how much? It's given to be, since this radius is given to be 25 meters. As we were given that the diameter is 50. So the volume of the outer sphere is 4/3 pi r cube. So r in that case is 25 meters plus 0.0005 meters cube. And since it's a hemisphere, so I only need half of it. Minus the original sphere. So that's the exact amount of paint you would need. But you don't want to, sometimes you are in a hurry and you don't need these exact kind of numbers anyway. So you want to use the linear approximation. And that's what the book asks you to do. That do a linear approximation to do this. And use the notation of differentials. So I just take this volume. I know that the volume of the hemisphere of a given radius is this. So it's just 2 by 3 pi r cube. I say that if I change the radius a little bit, I want to see how the volume would change. That's what the differential gives me. So remember, what was the differential? Was linear approximation. So this volume is a function of R. Right now I'm doing it in more detail because I'm just explaining, but then later on it will all become very like two-line calculation. So volume is a function of R, and instead of computing the exact things, I compute only up to linear order. So I expand or approximate by a linear function. Near my required any point. Let's call it R star, which for my case is 25 meter. Because I'm just moving a little bit away from this value. But I'm going to do it write it. I had done it in class, but I'm just doing it again. Around any special point. For me, right now, it's going to be 25. So I have it equal to V of R is equal to V of R evaluated at this special point plus the derivative evaluated at this special point and R minus R star. So this gives me this equation in the notation of differentials. This is just this. The linear change in function up to linear order. This is the value at R star. This is the value at nearby point. So starting from here, I just move to a nearby point of the radius. What is the change? What is the new value of the volume at a nearby point? There will be an exact value which I can compute from here. This is the exact value. But I just compute a linear. So let me write it L here, a linear approximation. So I get this. And this is just the derivative evaluated at your special point. And this, I just say that the change in the variable, because I moved a little bit from my special point R star to R. This is the change. And this change, linear change, I was writing it as dV. And to compute it, you see what you need to do. All you need to do is compute the derivative of the function at this special point and times the change in the independent variable. So I just take my formula. And do the differentials. So when you do the differentials, you do it as we did in class, as if everything is just the both independent and dependent variables are just variables, and you just do dV, derivative of this 3r square dr. And this dr for you is that small change, 0.00 0.05. So dV would be the paint required. And all you need to do is this 3 gets cancelled. Do these numbers, and this gives you a very good approximation of what you need. Wait. So there are some questions in chat. Okay. Okay, let me do some more of such problems. I had to put this. So let me, well, before I go on to, well, yeah, let's do this problem. So suppose you are given, I think I noted it down from the book. I'm not sure. Yeah, okay. So this is problem 37, exercises again, 3.10 from the book. It says use differentials to estimate, no, use differentials to find a formula for the approximate volume of a thin cylindrical shell with height h and inner radius r and thickness delta r. So you have a cylindrical shell. I know what's the volume of a cylinder. It's obvious. You just take the area of the disk and multiply it with the height. That's the volume of the cylinder. But you don't want that. You have a slightly thick, how do I draw it? So it's like a can, hollow can, and it has some thickness. So you want the volume of the hollow can. And the thickness you're given, this is h, and the thickness of the walls is delta r. So how would you find it? Well, volume of cylinder, as I have written, is pi r square h. And since I have thickened it, so I just approximate. So change in volume is what I get by the thickening using the differentials. H is a constant. I'm just changing the radius. Is this. Now here, dr I put equal to dr equal to whatever number I'm given. I'm not given any number, just like this. So this will then become the volume of thin cylindrical shell is about 2 pi r8 dr. That's the answer. So as easy as that. I don't know. Okay, so let me make a comment about it. So suppose what would be, if I try to find, this is an approximation. Exact answer is the following. Or true value What would be true value? Well, obviously it would be the volume of the outer shell minus the volume of the inner shell. So if I just open this square, I get r square plus delta r square plus 2r delta r minus r square. So I get 2 pi, these cancel, 2 pi r h delta r and plus this number pi h delta r square. So we had got this number and this was missing. So this is the error. And the error comes always at the next higher power. If you do the linear approximation, error will be quadratic. If you do the quadratic approximation, the error will be cubic.
So
And-
generally, what approximation should we do? Like if it's not written in the question.
Yeah,
what should we
I'm
assume?
not, excuse me. Well, I have said this so many times. I'm just here to explain things. I'm not here to tell you the tricks how to crack an exam. Okay, so if you ask me, this is not written in the problem, then don't do it. I'm just explaining something. So when you are, I'm just making a comment that this error, how do you know that this is small compared to this? Well, when you're comparing two numbers, always compare dimensionless quantities. So like this delta r, this is a thickness. This is something like a length, and this is also a length. So I can do this. I can, if I take r square outside, I get dr over r here, and dr over r square here. So now I'm comparing, I have taken all the dimensions here. This is length square, but this is, because when you're comparing lengths, you don't know how to compare a centimeter. This is a centimeter or a meter, and how to compare a meter square. That doesn't make any sense. You can't compare apples and oranges. But when I make it dimensionless over here, well, I can take 2 pi 8 outside as well. Now these are truly simple numbers. They have no dimension. Because this is length over length, so there's no length involved. Length over length, no length involved. So if delta r over r, this ratio of thickness to the radius, if this is small, if delta r over r is a number much less than 1, then delta r over r square will be even less than 1, and it will be less than delta r over r, because you know that this is the property of numbers less than 1, that if you square them, then you get an even smaller number. So if this is less than 1, then this is smaller than delta r over r, and approximation is good. So by making these dimensionless things, you can tell if you are doing something sensible or not. let me do this, for example. So it says find the differential of each function. Problem 11. If you have to find the differential of this is just dy is 2x sine 2x dx plus x squared. So what did I do? I'm using the chain rule here. So 2x dx sine 2x plus leave x squared alone and cosine 2x times 2. And since I'm differentiating something which is x, so I get a dx. So dy is 2x sine 2x plus x squared cosine 2x squared cosine 2x dx. So that's the differential. And this is also linear approximation around any point. So using this, if you want to open up linear approximation at x is equal to, let's say, a, so that would be plus this guy evaluated at x is equal to a, and dx is just then simply x minus a. All of this is a shorthand for this. So someone wants me to do questions from exercise 3.9. Yes, I'm going to do that. Let me just see if I need to do more from here. Okay, let me move to 3.9. But I'm just going to take some break. So I'm pausing the record. Let me do a few from exercises 3.9, and this is on related rates. Let's do first one of the very simplest one. So this is the problem 4. So it says that you have a rectangle and it has a length and it has a width. So the length is increasing at a rate of 8 centimeters per second, and the width is increasing at the rate of 3 centimeters per second. And they asked, what is the rate of increase of the area when the length is 20 centimeter and width is 10 centimeter. Well, so the area is length times width. So dA by dt is, so the point is that area becomes a function of time because length and width are a function of time. So dA by dt is simply dl by dt w plus L dw by dt. These two are constant. dl by dt is 8. You put in 10 for w. And then you have, well, it's a good practice to always put in the units. So this was 8 centimeter per second. And width is 10 centimeter plus 20 centimeter times the rate of change of the width was 3 centimeter per second. So it's simply 80 plus 60, so 140 centimeter square per second. That's the rate of change at this point. Now, let's consider this one. Problem 70, there's no 78 here. Let's consider this one 42. What do you mean? Why did I add the derivatives? I just computed. This was the formula for the area. Area is a function, becomes a function of time through length and width. So if I do how the area is changing with time, my chain rule tells me that I have to do this L times W. And the rule is this. Okay, so it says that a Ferris wheel with a radius, so you have this Ferris wheel. What's this doing? It has a radius 10 meters, is rotating at a rate of 1 revolution every 2 minutes. So rate of revolution is 1 revolution every 2 minutes. That means if I count the angle theta, this theta is changing. So there is some d theta by dt. Theta is a function of time because this rotates, and as a result of that, this theta from, let's say, from this horizontal x-axis changes. And it tells me that it covers 1 revolution in 2 minutes. And I have to use, if I'm gonna introduce the trigonometric functions and their derivatives, I must use the radians. So d theta by dt, what it is equal to 1 rotation is 2 pi radians change. And it says that it moves at a constant rate. So that means this d theta by dt is same at all times. So it's going to be a constant number. And what constant number? It completes changes in theta 2 pi per 2 minutes. That's the rate. So it's pi radians per minute. So d theta by dt is pi. And if you want, you can write radians per minute. People don't even write radians, just pi per minute. Pi angles per minute. So that's given to you. And then what you need to do is how fast is a rider rising when his seat is 16 meters above ground level. So this is 10. Face wheel is obviously like that. And his seat is 16 meters. So this is 16. That means that this is how much? 6. So if I call this length y and this angle theta, y is simply r sine theta. We want to know that at what rate this person is rising above the ground level. Standing from here, I don't care if this guy reaches here, that how much distance they have covered in this direction. From here to here, how much they are rising above. So all I need is dy by dt. So dy by dt is, and r is constant, d theta by dt. This is given to me. This is pi. This is fixed at 10 meters. What is the cosine theta? When his seat is 16 meters. So I need to find what is this theta when this is 6. So I have 6 over 10 is equal to sine theta. And so 6 over 10, so all I need is theta. I need cosine theta. So cosine theta is 1 minus sine square theta under root. So 1 minus 6 over 10 square. So you just find this number, plug it in here, and that will tell you the rate dy by dt. So any question? So let's look at problem 14. So you have a ship. It says at noon, ship A is 150 kilometer west of ship B. So you have this north, south, east, west. Is 150 kilometer west of ship B. Ship A is sailing east, So let me draw a diagram. Here is ship B and ship A is here. 150 kilometers away from ship B. And let's say this is at noon. So I'm going to call that time t is equal to 0 at noon. And ship A is moving this way towards ship B. Is sailing east, yeah. So it was towards the west of B and now it's sailing to the east. So it's moving this way. So I can call this x-axis and this direction y-axis, the usual ones to keep things simple. And I can call this point as x is equal to 0. So let's call this x-axis and this y-axis. And this point is 0, 0, where ship B was at t is equal to 0. And A was at I was 150 kilometer to the west on the negative x-axis and moving towards ship B. Moving towards east direction, so moving in the positive x direction. So I have, let's call position of ship A to be x of t, because it's only going to move along x-axis. So let's call it an x coordinate at certain time t, and position of ship B, because it tells me that the ship B is sailing north. So this is moving this way and ship B is moving this way. And this is 35 kilometers per hour. And this is 25 kilometers per hour. So I call position of ship B as y of t. Then whatever their positions are, they are with respect to this origin. The distance between them is still given by wherever they are. If I draw these x's again, doesn't matter where they are. Let's say this is ship A and this is ship B at some point. The distance between them will always be given by this formula. Because I put the origin in such a way, one is moving in the x direction, one is always on some x axis and one is always on y axis. So the distance can simply be given by this formula.
So why is there a plus in between?
What do you mean why there's a plus in between? If you have a point here and a point here, what would be the distance between them? Well, let's take it more generally. This is x-axis, this is y-axis. You have a point P. Its coordinates are x1, y1. And you have a point Q, any arbitrary point Q. Its coordinates are x2, y2. Then we know that the distance between them is given by the difference of the x coordinates plus the difference of the y coordinates. And since it's a square, it doesn't matter which coordinate you put first. Doesn't matter. That's the formula for distance between two. Over here, since ship A always moves in west-east direction, from west to east, so whatever its line of motion is, I have called it the x-axis. And since ship B moves in a perpendicular direction to that, south to north or north to south, wouldn't matter either. I have called that line, have they taken that line to be the y-axis. So ship B's x component will always be 0, and ship A's y component will always be 0. So I don't get this, and I don't get this. I get this. So that's what I have used. That's what I have used here. Is it clear?
Yes, yes, sir.
So I have got this. So now I just want to know how the distance between them is changing. So I just compute the derivative with respect to time. And I get, using the chain rule, uh, 2x of t dx of dt plus 2y of t dy of dt. Right. Now 2's cancel, so I can write now notice that all of these things are time dependent. So the rate of change of the distance between them is different at different times. The separation is changing, but it's changing at different times, although their own speeds are constant. But still you get this effect. Now the question is, how fast is the distance between the ships changing at 4 p.m.? So we need this guy, ds over dt, at t is equal to 4 p.m. So in other words, at t is equal to 4 hours, because I started t 0 at noon. So I need to compute this guy ds by dt at that. I need x of t and y of t at t is equal to 4. Dx over dt I already know. That's because that was fixed. That was 35 kilometers per hour. Well, actually, one has to be very careful in making this statement, because this rate of change, it is a sum of these two. So I have to be very careful about the signs, because if I don't get the signs right, I may be adding two numbers which need to be subtracted. So dx by dt is change in x coordinate with respect to time, and it's a plus. And why it's a plus? Because I'm moving in this direction. So I make these small changes, delta x, and so dx by dt is a plus because the x coordinate of the ship A is increasing with time, since it's moving in the east direction. Similarly, dy by dt is also a positive number because the ship is moving in the north direction. So its y coordinate is increasing with time. So dx by dt has to be taken 35 and dy by dt is taken to be 25 hour, and we need to find these guys still. So that one can do by simple logic. When we will study more, we will see that how to get these things using integration. But over here, we haven't done that, but it's very simple logic, so we can use that. Ship B at t is equal to 0 started at minus 150. At t is equal to 0, x of t, which is x of 0, is minus 150 kilometers. So in t is equal to 4, I should get minus 150 kilometers plus, since it covers 35 kilometers in an hour, so it must have covered 140. So it's minus 10 kilometers. That's its position. And similarly, at t is equal to 0, y of 0, that was taken to be 0. So at t is equal to 4, y of 4 is 25 kilometers in an hour, so 100 kilometers. So I put these back. Let's call it A. Put these numbers in equation A. So you get something like 1 over minus 10 square plus 100 square, and this is all a kilometer square. Then you have a minus 10. Now this is crucial. You're not adding these two numbers, you're subtracting. Minus 10 kilometers times 35 kilometers per hour plus 100. The y number was positive. The units appropriately cancel to give you kilometers per hour as it should. And these numbers you have to do in a calculator. So I get 2500 minus 350. So 2150 divided by square root of 110. No, square root of 100 square is 10,000 plus 100, and the square root of this is about 100.5, almost, not exactly. So this gives some number 21.39 kilometers per hour. That's the rate of change of this separation. Now let's try this 15. Well, the significant figures are not very important here unless they're mentioned. We are not doing any physics. We are just having ideas about how to deal with problems. So not very important. Okay, so problem 15 says that two cars moving from the same point. One travels south. At 60 miles per hour, while the other travels west at 25 miles. And they both start from same point. So that means at t equals 0, I can draw as usual the x and the y. This is x, this is y axis. And this is the directions of motion. So at t equals 0, well, again, I can say position of car A. I'm gonna represent it by x because it has only x component. If you want, you can write it like this. Because I know that the y component of car A is always 0 and the x component of car B is always 0. Wait. I did it so I'm calling this car A and this one car B. Then it makes sense. Right. So, and the question is that at what rate is the distance between the cars increasing 2 hours later? So again, the distance is simply x squared of t plus y squared of t. And we need this ds by dt. So again, it's gonna come out to be x dx over dt plus y dy over dt. This guy always has this formula for derivative. And at what rate is the distance between the car increasing 2 hours later? So at t is equal to 2, x of t, which is this guy, some number here, because it moves at 25, so it's minus 50 miles. And y of t is how much? It moves at 60 miles, so it's minus 120 miles. Y coordinate is negative if I draw the axis this way. While if you look at dx over dt, since it's moving in this direction, its x coordinate is decreasing with time. So this speed is actually should be taken minus. And similarly, dy by dt, according to this choice of axis, should be taken minus 60 miles per hour, because the y coordinate is decreasing with time, not increasing with time. So now all you have to do is put these numbers here. And since all of these numbers are minus, so these gonna be, both of these gonna be plus. And you can just compute. Let's look at 24. Yeah, T is in hours. So a trough is 10 feet long. It's like this. Like this, something like this. And it's being filled with water. And if I look at it from this angle, something like this. This is its cross section. And I'm told that, so this length is 10 meters, 10 feet. And this side, this is 3 feet, this thing. And this is and this is 1 feet, this height. Well, the water starts filling like this. At some point, it's like this. And if you look at a later point, it's like this. So if you look at the cross section, the volume of water always makes this kind of isosceles triangle. The difference would be that at a given time, the isosceles triangle will have a different height and a different base compared to the full size of the trough. But it's going to be a similar triangle because it's the same triangle which you are filling up. So it's going to be a similar triangle. So if I denote the height of the water by 8 and this by base B, then the volume is simply going to be the length of the trough times the area of this. And the area of this is obviously, because it's an isosceles triangle, B times 8. Right, because this is a perpendicular, so that's the B times 8. Now the thing is that I can write the B in terms of h, because I know that in the original thing, I have B over 8 should have same ratio as 3 over 1. Since the cross section of trough and the water triangle are similar triangles. So you have this. B over 8 is same as 3 over 1. So from here, you can say B is 3/8 and put it here. Because the point is that when the water rises, 8 changes, but so does B. So they're not independent. So you have to take care of that. So you get 3L 8 square. And now I can find, because L is constant, the rate of change of how much water is going in is 3L times 2H dH over dt. So these two rates become related. We are given this So this is told us that this is how much water is going in per time. That's just a fixed volume, is 12 feet cube per minute. You put that in there, and length was 10 feet. And you have to find this guy. So you solve for this, solve for it by putting 8, because you are finding it at a one particular time when 8 is 6 inches. So 0.5 feet. And you just solve for it. You get your answer. So slightly difficult one is the next one, 25. A water trough is 10 meter long and a cross section. So again, this is some kind of a trough. There's a certain length, 10 meter. Is this cross section, which I'm looking at? It says that it's a trapezoid whose base is 30 centimeter and 80 centimeter at the top, something like that. And has height 50 centimeter. So this is 50. Something like that. So this is 30. Then this side would be 20, this side would be 20. And you are filling in water like that. So one can think of it that when you fill in, I can think of this part to be separately filled, this tube to be separately filled, and this tube is being filled, and this tube is being filled. So this guy and this guy, I can think of them as one thing, joined as one thing. So this becomes an isosceles triangle of base 40 and height 30. And then you have a rectangle of base 30 and height 50. So that means the volume, total volume which is filled at a particular time is going to be the length times the volume of this rectangular tube, which is, this base is fixed. Height keeps changing with time. Plus, you have to add the volume of these triangles, which in this b over h is now 4 over 3. So b is 4 over 3h. So it's length times h square times 4 over 3. Just using this previous formula, length times b times h. And you're adding these two. And length was also given. Well, this was actually 30 centimeters, so this is like 0.3. So length is 10 times 0.3 times h of t plus 10 times 4 over 3 h of t square. So now you do dv over dt, you get 3, and derivative of h is just 1. And here you get 40 over 3 times 2 h of t, and you have to find h of t times dh of dt. Well, this guy was 3 dh over dt, not 1. 3 dh over dt. So you get 3 plus 80 over 3 h of t dh over dt is dv over dt. This is given to you. This was a fixed rate. It's being 0.2 meter cube over per minute. And you have to find when this is 0.3 meter deep. So you put this in and solve for it. So any question? Let's do 43. So there's a ground radar station here and a plane directly above it is at an altitude of 1 kilometer, and it's rising at an angle of 30 degrees, and it's moving at, well, let me draw it this way. It hasn't shown me a direction, so it will be more intuitive to consider it this way. 30 degrees, and the speed is 300 kilometers per hour. At what rate is the distance from the plane to the radar station increasing a minute later? So if what I can do is take this to be origin, this to be x-axis, and this to be y-axis. So then at any given time, the plane has coordinates of plane x of t, y of t, and coordinates of radar are fixed. They don't change with time. They are 0 and -1. I'm doing it in kilometers. So the distance is x square plus y minus -1, so y plus 1 square. And what you need, so let me write it clearly. X of t square plus y of t plus 1 square. So then all you have to do is this. Sometimes I write the dependence, sometimes I don't. You got 2x dx over dt plus 2y plus 1 dy over dt using the chain rule. And you got now you have to tell the at what rate is the distance from the plane to the radar station increasing a minute later. So you need this rate at t is equal to 1 over 60 hours. Why have written y of t plus 1? Because I just made this x-axis, y-axis. So the coordinates of plane are, at any point, I can resolve them. They're going to be x of t and y of t. I've written here, but the coordinate of radars are 0 and -1. So I need this plus 1 because I use the distance formula, difference of the x coordinates and difference of the y coordinates. Okay. So at t is equal to 1 over 60 hours, I need x of t. So x of t is just simply 300 times cosine 30, and y of t is 300. You have to put the units in. I'm just not writing them for now. Sine of 30. You get these numbers, put them here for x and y. Dx over dt is again 300. Oh, sorry. This is dx by dt. Because you have a speed and you're looking at it's how the x and y are changing. So you're just resolving the speed along dx by dt and dy by dt. You've got this speeds along x and y, so you can now find x of t at 1 over 60 hours. All you have to do is multiply this speed by time. So take these numbers, put them in. Similarly here. dy of dt, which you will find by multiplying with the sine theta, times 1 over 60. And put that all these in here, and you will have your answer. We can do one last one. Let's look at this problem. 45. So our runner spins around a circular track of radius 100 meter. is the track. And this is 100 meter. The owner's friend is standing at a distance 200 meter from the center of the track. So at some distance, and I can draw the straight line from the center to the friend and call that to be x-axis. So this distance then that means is also 100, and this is 200. How fast is the distance between the friend changing when the distance between them is 200 meter? So the friend, they are running like this. So there will be some point here. So let's call the friend this person A and this person B. Now I can put the origin here. So then the coordinates of A are 100 cosine theta, if this is theta, and y is equal to 100 sine theta. And these are not constant, because theta is a function of time. They are running around. So I can write the distance, which is going to be again a function of time. Coordinates of B, let me write those. Because the way I have drawn the axis, the coordinates of B are 200 and 0. So the distance is simply the difference of the x coordinates. So that is 200 minus 100 cosine theta square and plus 100 sine square theta. So if I want, I can probably open this guy, 200 square plus 100 square cosine square theta minus 200 square cosine theta plus 100 sine square theta. The only nice thing is I have got rid of these two guys. And I have got, these becomes 100 square. So 200 square plus 100 square, you can add these guys. Plus, I've got minus, I have got 200 square cosine theta. So I have to do only one differentiation of one trigonometric function. So you can now do ds by dt. Let's call these numbers a and b. A minus b cosine theta. It's d by dt of a minus b cosine theta. So this is 1 over 2 a minus b cosine theta times the derivative of inside, which is minus b times minus sine theta d theta by dt. So what is d theta by dt? This should have been given to us if we want to compute this. And they tell us at a constant speed of 7 meters per second. So the circle had a radius of 100. So the circumference is 2 pi times 100. Was it 100 or was it 10? 100 is this. And the cover speed is 7 meters per second. So if I take the ratio, how many radians they cover in a second? So 7 over 2 pi times 100 radians per second. So this is d theta by dt. You put this in here, and you're doing it from one particular point. Compute theta of t when this s, whose formula is given to you, and s is equal to 200. Or I had got the formula simplified to this. Put this equal to 200 and compute what theta will give you this 200. Do the inverse, find the inverse theta angle and put that in. Now put these numbers in here, the theta value and the d theta by d2 value. You don't need the theta value directly, you just can compute cosine theta and from that sine theta and put this here. And that's how you got it. Not putting in the numbers, you can do that yourself. So any question?
No, sir.
Anyone else has a question or some comment? Okay, let me end it here.